This video presents a full implementation of an encoder-decoder AI transformer in C++. Billy will first give you an introduction and a concise review of an AI transformer.
This is a follow-up to our previous video, which has discussed the implementation of a GPT-style transformer in C++. We have covered most of the underlying programs in the previous few videos, which could be found at this link. Here, we bring them together to implement a complete encoder-decoder transformer in C++. We also provide some simple training examples. When executed, the program prints the entropy loss at selected epochs. The first example trains the transformer to translate English digits 1, 2, 3, 4 to the corresponding Spanish words, uno, dos, tres, and cuatro. As you can see, the loss decreases steadily over the course of training. After training, when we input English words 1, 2, 3, 4, the model generates their Spanish equivalents, uno, dos, tres, and cuatro as expected. The second example trains the transformer to reverse the sequence 1, 2, 3, 4. As expected, the transformer outputs 4, 3, 2, 1. The loss also decreases steadily over the course of training. The third example trains the transformer to output digits 1, 2, 3, 4 from the words 1, 2, 3, 4. Again, the loss decreases steadily over the course of training. Let's first have a concise review of a general transformer and discuss the implementation of a Encoder-Decoder transformer. This figure illustrates the transformer architecture. On the left is the encoder, which repeats 6 times. On the right is the decoder, also repeating 6 times. Thus, we have 6 encoder layers and 6 decoder layers. If we expand the encoder stack, it looks like this. Input goes to encoder layer 1. Its output feeds into encoder layer 2, whose output feeds into encoder layer 3, and so on. The final output of encoder layer 6 is E, and as shown, E is passed to the multi-head attention blocks of all decoder layers. This vector is fed into the multi-head attention mechanism of each decoder layer. The external input to the decoder is X, which is generated from target input. The output at the first block of a decoder layer is X1, the output at the second block is X2, and so on. We can label the output of the final block as X3, or Y. It becomes the input to the next layer. The output of the last layer passes through a linear layer and a softmax. The probabilities generated by the softmax function are compared with the target output to obtain a loss gradient which will be used for backpropagation. All decoder layers operate in parallel with respect to receiving E, but sequentially in terms of their own internal connections. Note that only the final output, that is, the output of decoder layer 6, goes to the linear and softmax layers. That, in essence, is the basic architecture of an AI transformer. After embedding and positional encoding, a transformer begins its forward computation starting from layer 1, passing outputs sequentially to the next layer, as illustrated in the figure. The encoder's final output, E, is used as the key and value inputs to the decoder's cross-attention blocks. Once forward computation is complete, the transformer performs backpropagation to update all weights and learnable parameters. It uses the difference between the softmax output probabilities and the target output to compute a loss gradient. This gradient updates the parameters of the last layer and is then used to compute another gradient for the layer below, repeating this process down through the network. Let's review how backpropagation works. During the forward pass of a block, we compute an output matrix Y by multiplying the input matrix X by a weight matrix W. That is Y equals X times W. Given the gradient of the loss with respect to the output, dl/dy, we can compute the gradient with respect to the weight matrix dl/dw by multiplying the transpose of x by dl/dy. The weights are then updated using dl/dw using these formulas. In addition, the gradient with respect to the input, dl/dx, is obtained by multiplying dl/dy by the transpose of w. This gradient dl/dx becomes dl/dy for the preceding layer. That is the next stage in the backward pass as shown in this figure. The figure below shows the output layer of a transformer corresponding to these components in the transformer figure. The right side shows the corresponding C++ code that implements this layer. Dout is the output form the last decoder layer. It is the input to this output layer and we refer to it as x. In the forward computation, we multiply x to the weight matrix W to obtain the logit C, which is fed to the softmax function to generate the probabilities P. In our code, the forward function returns the probability matrix P. The cross-entropy loss L is computed using the target output matrix T and the probability matrix P. The loss gradient dl/dy is computed by this formula. It is equal to P minus T, or the code here. As mentioned earlier, dl/dy is used to calculate dl/dw, which will be used to update the weight matrix W. Also, we could calculate dl/dx, which is equal to dl/dy times W transpose. The backprop function returns dl/dx, which becomes the dl/dy or output gradient for the backpropagation of the presetting stage, that is, the last decoder layer. When the final decoder layer receives the dl/dx from the output layer, it begins its own backward computation. During the forward pass, each decoder layer takes two inputs, x from the previous layer and e from the encoder as illustrated in the figure. Consequently, during backpropagation, each decoder layer must compute two gradients. dl/dx, which is passed to the preceding decoder layer, and dl/de, which is passed back to the last layer of the encoder. Since all decoder layers receive the same encoder output E in parallel during the forward pass, each contributes to the total loss. Therefore, the gradients dl/de from all decoder layers must be accumulated before being passed back to the encoder. This similar to the case that y1 equals f1e and y2 equals f2e. The loss L is the sum of y1 and y2. He gradient dl/de is equal to dl/de via y1 plus dl/de via y2. The following code shows how this could be implemented. We first obtain the dl/dx from the output layer. We then iterate through the backprop function of the decoder layers, starting from the last layer. In each iteration, we get a new dl/dx which will the input to the layer below. We also get a dl/de. We add this new dl/de to what has been accumulated. Using the function add, mat. The loss gradient with respect to the encoder output E is the accumulated dl/de from the backprop of the decoder. This accumulated gradient is then passed back to the last encoder layer to begin backpropagation through the encoder. During the forward pass of the encoder, each layer has only one input x. For example, x0 is the input to the first encoder layer, which produces x1 as input to the second encoder layer, and so on. In general, layer L receives XL and outputs XL plus 1. During backpropagation, this process is reversed. Starting from dl/de, the gradient flows backward. dl/dxl plus 1 is used to compute dl/dxl for each successive layer. The following code shows this flow. In our notation, x often denotes input and y denotes output in the forward pass. In the backward pass, this is reversed. dl/dy, the output gradient, is dl/dxl plus 1 and is the input. It produces the input gradient dl/dx equal to dl/dxl, which becomes the output of the current layer or the input to the layer below. The following is a full implementation of this transformer. util.h is the header file of the helper functions. util.cpp is the implementation of the helper functions. Some functions are presented for your reference. They might not be used in the implementation of our transformer. We have discussed most of these functions in previous videos. We'll only discuss them very briefly here. F is a ReLU activation function 1 double input. ReLU is the ReLU activation with matrix input. ReLU_deriv is the derivative of ReLU. Cross entropy calculates the loss from the probability matrix P, which is the output from softmax, and the target output. AddMat adds two matrices. Transpose returns the transpose of a matrix. MatMul returns the multiplication product of two matrices. Scale mat multiplies each element of a matrix by a constant s. Mul_mats returns a scaled matrix without altering the input matrix. Init matrix initializes a matrix with random values. Softmax is the softmax activation function. We overload this function. Its input could be a 1D vector or a matrix. Softmax derivative implements the derivative of the softmax function and returns the derivative function values in a matrix form. The following are the classes we have discussed. This is the header file of the transformer classes. These are the implementations of the classes. This is the tokenizer class, embedding class, positional encoding class, add and norm class, feed-forward class for the feed-forward network, multi-head attention class. Its member function compute attention can compute the attention with or without a mask. The backprop member function returns a gradient struct consisting of the gradients with respect to query Q, key K and value V or DLDQ, DLDK and DLDV respectively. This is the encoder layer. The output layer. The decoder layer. The is a mini transformer class. It has an output layer named output, and encoder layer and decoder layer objects are saved in the vector Z layers and D layers respectively. There are totally n layers of encoder and decoder layers. The forward function returns the probability matrix, which could be used for backpropagation or inference. The train step function is one step of training the transformer as discussed. The generate function is for inference. After training, it will predict the output with a given source input. Finally, this is the main program for testing our transformer. As a demo, we first build a data set with a tokenizer. We define a struct named training_ds as shown. We have three examples. The first example has source data 1, 2, 3, 4 and the target output 1, 2, 3, 4. The second source is 1, 2, 3, 4 reverse, and the target output is 4, 3, 2, 1. The third source is 1, 2, 3, 4 digit, and the target output is the Arabic digits 1, 2, 3, 4. These data sets are returned as a vector training_ds struct. In the main, we create the tokenizer using the vocabulary in the file t.txt. The model we use will have a sequence length of 16. The dimension of the model is also 16. Number os heads is 4. Feed-forward network dimension is 16. The number of encoder and decoder layers is 4. The learning rate is 0.02. We'll train the model for 601 times. After the training of each dataset, We do the inference using the source of the data set and compare the generated result and the expected result. Let's copy and compile these files and run the resulted executable to see how it works. We've copied the files to this directory, including util.h, util.cpp, transformer.h, transformer.cpp, test main, the make file. Let's take a quick view on them. The vocabulary file t.txt contains the vocabulary and will be tokenized to integer tokens in the tokenization process. The detokenization process converts the token integers back to words. Now let's compile them using make. As you can see, the executable test main is created. Let's execute it. In the first example, after training the English words 1, 2, 3, 4 are translated to Spanish words uno, dos, tres, and cuatro as expected. The entropy loss decreases steadily over the course of training. In the second example, the trained transformer reverses the words 1, 2, 3, 4 to 4, 3, 2, 1 as expected. The entropy loss also decreases steadily over the course of training. In the third example, the trained transformer translates the English words 1, 2, 3, 4 to Arabic digits 1, 2, 3, 4. The generated output matches the expected ones. The entropy loss again decreases steadily over the course of training. We can conclude that the transformer implementation is correct. You can try it yourself by adjusting the parameters and training examples to gain a better understanding of how it works. To explore further, modify parts of the code or try improving upon it. If you find any bugs or have feedback on the implementation, please leave a comment in the comment section. This wraps up our discussion on the transformer. Thank you for watching and for your support. Goodbye.